Okay, in example number 3, we want to be able to rotate about the y-axis. We're going to find the volume of the solid obtained by rotating the region bounded by y is equal to x cubed, y is equal to 8, and x is equal to 0 about the y-axis. So if you look at our two-dimensional figure in figure 8, you can see here that here we have y equals x cubed. We have our horizontal line at y equals 8, and then we have our vertical line at x equals 0. And this is the surface that we're looking for. Now, what we're doing is we're rotating it according to the y-axis, which is the reason why we get this type of solid here. Now, what we do is we're creating a circular disk, and that circular disk is going to have a radius of the cube root of y. And the reason why it's the cube root of y is because we want it in terms of y. So what we're going to do is we're going to solve this equation for x. So the region that's shown in figure 7a, and the resulting solid is shown in figure 7b. Again, because the region is rotated about the y-axis, it makes sense to slice the solid perpendicular to the y-axis and therefore to integrate with respect to y. Now, if we slice at height y, we get, again, a circular disk with radius x, where x is now equal to the cube root of y. So the area of the cross-section through y would be the following. Area with respect to y is equal to pi x squared, but we know that x is going to equal to the cube root of y. And if we square that, we get pi y to the 2/3. And the volume of the approximating cylinder pictured in that figure would then be pi y to the 2/3 times delta y. Now, since the solid lines lie between y equals 0 and y is equal to 8, we know that our lower limit is 0, our upper limit is 8 of the function pi times y to the 2/3 dy. Taking the antiderivative of that, we get pi times 3/5 y to the 5/3, evaluating it with a lower limit of 0 to 8, which gives us a volume of 96 pi over 5.